Hi guys. I'm just wanted to give a couple of minutes to see if we have any more people coming. Can you please confirm that you can see the PDF with the questions for the tutorial in the screen? Please give me an okay in the chat. I would appreciate it, and I'll give you 1 or 2 minutes, and then we'll start. And that okay. Thank you. By the way, let me share the link to CodeShare that we're gonna use today. And I will be pasting the R script that we're gonna need there. So you can go and grab that. Please, again, don't cut, just copy from CodeShare and bring it into your script, like a fresh R script. And here's the link also. If you can see it in the website, if it's too small in here or something. So please don't forget to grab it and put it in a fresh R script. Okay, I think we can start. So today we're going to discuss dynamic relationships. In particular, we're going to be focusing on an ARDL model. ARDL stands for Autoregressive Distributive Lags model. This model allows us the study of the dynamic relationship, right, between two or more time series, and we put them all into the same model. And the way this works is that we are explaining how one time series evolves, that time series evolves depending on how it behaved previously, so on lags on itself, and on current and lag values of other variables. Okay, so we can bring more than one, more than two actually, like a difference to the ARMA model, which we can only work, or we could only work with two variables, right? In this case, actually with only one, sorry. In this case, we can add two or more. And another good thing is that we are not necessarily assuming that these time series are stationary. ARDL does not take that into consideration. We do assume white noise residuals. So that's something that we are going to check. And so that's for the ARDL. And the main source of analysis for dynamic relationships are the impulse response functions. So we're going to learn how to generate those impulse response functions. What do they mean? And yeah, how can we interpret, right? So the first thing that we're going to do today is to derive the ECM representation of the ARDL 112. So the ARDL 112 model means that a variable is explained by one lag of itself. The first index is always corresponding to the dependent variable. So one lag of itself one lag of the of an exogenous variable, in this case x. So we will put x in contemporaneous values and x in lag in only one lag, and two lags of another variable, in this case w. So we have wt, t-1, and t-2. That way we can explain changes in yt using different dynamic of more than two variables. And of course, as you add more variables, before I forget this, you will add more indexes here. So it's not bound to be 3. If we are analyzing 5 variables at the same time, then we will have 3. We will have 5 numbers in here, right? And we're going to work from this ARDL representation into the ECM representation, which stands for error correction model. The error correction model allows us to analyze the dynamic between these variables in the short run and in the long run. So we can identify, like, without much trouble, if these variables, sorry, my throat is a bit sore today. If these variables share a long run equilibrium, and you know, a lot. I don't want to get ahead of myself, but there is a lot of inference to grab from there. So we will analyze them when we get there. But for now, let's see how we do this transformation, right? And yeah, and we are going to identify what are the long run multipliers and adjustment parameters. So I will get to that in a second. So let me jump to the slideshow. You guys should have it there. Again, none of these is in kosher, right? This is just work that we're going to do. But you know, like it's going to be helpful, like to get this step by step. So again, I won't be able to share these slides for you online, but I will try to go as slow as possible to show you, and like you can come back to it and try it on your own. So before we do this transformation, we need to find a few terms that we're going to add and subtract to this equation, right? By adding and subtracting the same value, or you know, the same term, we are not messing with the balance of this equation. And like then with the we rearrange some values there, we can get to a completely different specification, which allows us further analysis that's very helpful. So a couple of tips, because I think you will, yeah, I think you will be able, or you will be required to do this process. So that's why I will try to go as slowly as possible. The first thing is that we always, oh, sorry, my computer is a bit crazy today. We are always going to add a term that we're going to name gamma, which is just something that we're going to use as an intersect later. Okay, so we add and subtract that term. We add and subtract the first lag of the dependent variable, hence yt-1 here. And then we are going to add one term for xt. In this case, we'll start with the first lag of xt. Like we take this term and we calculate the first, or we operate the first lag of this term. Same for wt, but in this case we have two lags, so we take the first term and we find the first lag of this, like we did with x. And if we add a second lag, then what we do is that you move to the next index, like yt-1, but you grab the coefficient of yt-2. So there is a method to note how or what of these terms to add. the first thing that you need to note is that we have like these indexes add up to 4, right? That means that we will add 4 terms here with the variables, and always plus or minus gamma, but we don't count that. So later, again, getting a little bit ahead of myself, I will show you like the transformation from a 1 to 2 model. I will leave it there for you, so that way you have 2 examples and you can work and practice this. So we add and subtract these terms, so plus and minus gamma, plus and minus yt minus 1, plus and minus b0 xt minus 1, plus and minus c0 yt minus 1, and plus and minus c2 wt minus 1. Okay, so we are going to now to rearrange these terms. The first thing that I do is that I take this yt minus 1 positive, and I send it to the other side of the equation to subtract with yt, because I want to obtain delta yt, right? And that's the way it is calculated. And then I am going to kind of group by well, let me see the ordering first by yt. So I take the remaining terms that I have that have yt on it. So I have negative yt minus 1, and I have alpha a1 yt minus 1. The next thing that I'm going to do is to group by constant terms. So I have a0 with the negative gamma, right? I'm going to leave the positive gamma here first. I'm going to again group, but in this case by xt minus 1. So I'm going to take this positive xt minus beta b0 xt minus 1. Where else is xt minus 1? It's in here, b1 xt minus 1, and it's nowhere else. So I will jump now to wt minus 1, right? So c0, the positive, yt minus 1, c1, yt minus 1, and c2, yt minus 1. Those are those 3 terms in here. And afterwards, I'm going to group by coefficients. Like if you notice, let me select this to note the terms that I'm already using. If you notice here, the terms that are common here are beta 0, c0, c2. So I'm going to group by coefficients. So b0 xt, negative b0 xt minus 1, c0 wt, negative c0 wt minus 1. And in here, I have negative c2 yt minus 1 plus c2 yt minus 2. So the positive terms, these terms that I added, so b0 xt minus 1 and c2 yt minus 1 and c0 yt minus 1, those positives will be grouped by variable, and the negatives, right, will be grouped by coefficient. Now here I'm going to take just a bit of factoring. I am operating these terms of yt minus 1, so I'm grouping by yt minus 1. So I have, and if I take a negative outside the equation, I have 1 minus of 1, or a1. I'm just putting these 2 in a bracket and nothing there. Don't worry about the gamma. Gamma will be an intersect, so gamma won't be worked further than just leave the positive there, and the negative will be grouped with alpha c, with ac, the intersect of the original expression. In here, I can group by xt minus 1, so I'm doing that, b0 plus b1. And in here, I'm grouping by yt minus 1, so I have c0, c1, and c2, all of this in the bracket. In the other terms, the common term here is the coefficient, so I'm grouping by the coefficient. So I'll be left with xt minus 1, which, of course, you guys remember will be equal to delta xt minus 1. In here, I'm grouping by c0, so wt minus 1. Of course, you know, delta yt. And finally, I am grouping by c2. So I have c2, And this in here, I need to do a little bit of a trick because I want delta yt minus 1, and delta yt minus 1 is yt minus 1 minus yt minus 2. But yt minus 2 is positive, and yt minus 1 is negative. So if I take -1 outside of this bracket, I can invert the signs of this. So this bracket will give me the result that I'm looking for. And please note that that sign will be changed. Moving forward, I think, oh yeah, I'm just doing the operations that I mentioned before. And now I am also doing this operation, right? Yt minus 1 is equal to delta yt. Other than that, let's move forward now. This trick now, sorry. Everything after this, I will not work no more. So this will not change, but I need to rearrange and gamma won't change. I need to rearrange this in order to get the terms that the ECM representation requires. In order to do that, I will take this coefficient of yt minus 1, so -1 minus a1, and I am going to multiply and divide each of the terms that I have here by this term. Of course, multiplying and dividing by the same term, it's equivalent to multiplying by 1, which again will not mess with the balance of this equation, but will allow us to do something. So yeah, that's what I'm doing. Taking this coefficient, -1 minus a1, multiplying and dividing a0 minus gamma, b0 plus b1 times xt minus 1, and c0 plus c1 plus c2 times yt minus 1. I'm doing this because having that term there allows me to factor this term out of each of these terms here, right? I'm just taking this, let me go back for a second. I'm just taking these numerators and factoring all of those terms into the same bracket by that term. Again, everything else will not be changed. The next thing that I'm going to do is operating the signs here. So a positive sign divided by a positive term divided by a negative term equal to a negative term. So I'm changing the negatives there. And now I'm going to give some names to my ECM representation. So the ECM representation is this one. I'm going to call this term that I use to group all of these as alpha, right? This term in here, I'm going to call it mu. This division here, so b0 plus b1 divided by 1 minus i1, I'm going to call it beta x, and all of these, I'm going to call it beta w. Okay, alpha is what we call an adjustment parameter. Mu is the constant of the long run term, and beta x and beta w are the long run multipliers of x and w on y corresponding. And one interesting feature of the ECM representation is that it allows you to analyze the long run effects of the variables on yt and the short run effect of those variables on yt as well, right? So yeah, so this short term is how yt, like how yt responds to changes in xt in yt and yt minus 1. I have two terms. I have one term on xt and two terms of yt as it was planned in the model, right? So 1, 1, 2. So I have 1x and I have 2 w's as it was stated. And the long run, well, the long run multipliers will show me how yt will respond in the long run, how will it change in the long run if xt or wt suffer any sort of shocks, meaning unexpected increments or decreases, right? Yeah, like I mentioned, mu is just a constant term in the long run bit of the ECM representation, and alpha is what we call an adjustment parameter. An adjustment parameter, wait a second. An adjustment parameter allows us to analyze if the variables share a long-run equilibrium. If the variables do share a long-run equilibrium, alpha will be a negative number. The software would already take this negative into consideration. So whatever number we get for alpha, we look at the sign. If alpha is negative, these variables share a long-run equilibrium, meaning that they kind of wander in following similar paths over time. And one shock in one of the variables will cause YT to drift from that path, but eventually it will return to it. And the magnitude of alpha is how fast it will come back to equilibrium. So higher alpha is going to be a 0 point something number, to put it in easier terms. So yeah, large alpha will mean that after the shock, YT will come back to the equilibrium with the other variables rather fast. I'm going to add another example of this in the recording. I have it here on my slides. So I wanted to leave a couple so you guys can practice and you know, have familiarity with the process in case you're asked to do that in an exam. Oh, wait, sorry, before I forget, beta X and beta Y, the long-run multipliers, they will capture all the effects that X, for example, X has on Y over time. And beta W will capture all the effects that WT has on YT over time. Okay, now this is getting ahead, so let's go back to the slideshow. Now, remember that I mentioned that we're going to study this dynamic relationship using IRFs. Well, we need to, or we are asked to generate or create a function that will allow us to compute those coefficients, like to compute the terms in the IRF. So let me show you what we're going to do. This is in lecture 3, slide 7. We're going to apply the method of undetermined coefficients. With this method of undetermined coefficient, what we do is that we take two variables and we take the terms of those variables, the coefficients of those variables, doing some operation. Actually, the operation is here. We will get all these terms, all these thetas, which will correspond to the response that one variable has to shocks of the other at a determinate point. So gamma 1 will be the response to a shock in that, in this case, let's call X and Y, that Y will have after, like on the first period, after X suffers a shock, theta 2 will be the response of Y to a shock of X, an unexpected shock of X, 2 periods, but they are not cumulative, right? They're just the single response to shocks 1, 2, 3, 4, and whatever horizon you set after the shock has occurred. Okay, so we want to do this, and we want to do it in a function. That way, we will just change the parameters, and it's like we can replicate it over and over again instead of having to rewrite the code. So I think that's a good practice to do. And R allows us to do that. So let's jump to R now. Please, again, copy your code share code in a new R script, set up working directory, and make sure, please, that you download, let me display this real quick, that you download, it's not this, these 3 files, these 2 files actually, ARDL underscore IRFs underscore CIR and wealth.csv into your working directory as I have it in here, right? We will need this R script and we will need this data set in it. Everything else is just additional stuff that I have there. So make sure you do that. And also, if you don't have it, make sure that you have installed the ARDL package. You can see it here on my list. Actually, by the way, I just want to mention I'm having problems with. Wait, just give me a second, please. I'm having problems with my internet connection. I'm getting the message in here. So if you like see that my image gets blurry or something, my apologies in advance. I'm like hoping that the problem won't get too bad, but it's that like the situation I'm having with my internet at home since the flooding is being quite weird. So I hope it's good. All right. So if you don't have the package installed, make sure you use the install packages. If you do have it, don't do this, please. But we do need to activate the package. So in order to do that, we use the command library, or you can just come to the package list and tick it. Okay. If you put a tick there, that means that it's ready to work. Now, let's build a function to calculate these thetas, right? These thetas are calculated by pretty much dividing, where's the lecture slide? Pretty much dividing the terms, the coefficients for one variable by the coefficients of another variable, right? So we want to capture those coefficients. We want to divide by that, and we also want to set up a horizon, right? We want to see if it's no, sorry, we want to see how they evolve over a horizon that we set. In our case, well, we will set up with the argument h. So a is not going to be a number, it's going to be a vector, right? So I don't know if a has 3 terms, so like, yeah, whatever, like the dependent variable in this case, we added 3 lags of it. We will have 3 terms in that vector that will be input here in A, and same for B. So the first step for this function is calculating. Let me move to the next one. Sorry. The first term that we calculate is just the constant terms of those two variables. So we will grab the first term in the string of characters for beta, for B, and divide by that. So like in coefficients, the first coefficient is always going to be an intersect. So we are going to divide those intersects in here. Now we can have the possibility that the horizon that we set, it would be equal to 0. It makes no sense, right? Because we want horizons to be large in order to see how the impact, so how the function responds to impacts over time. But in computational terms, we do need to prepare for that, because in case someone actually inputs a 0 just to try what happens, our function will crash. We don't want that. So if the horizon is equal to 0, then we will just be displaying whatever theta 0 we got from here. And that's the whole response that we get, which is not informative, but we need to do it. Then we're going to capture the orders of these 2 coefficients, meaning how many coefficients do we have in it? Because we're going to compare if, well, actually, starting with B, we're going to compare if the terms in the polynomial A is higher or not than the horizon that we set. Because if we have more terms in the horizon than lags in the equation, we will need to add like we need all these terms H, P, and Q to be of the same length. So we will just add extra empty values here for A. So with numeric here, it pretty much adds new vector slots equal to 0, and it will add as many as we specify here. So in here, I'm just adding the difference between how many terms the horizon has and how many terms the polynomial A has. And we will do the same for polynomial B. And well, afterwards, after like from theta 0 onwards, right? The first term in our theta mate vector is going to be theta 0, and afterwards we're going to add 40 zeros because we are going to add theta 1, theta 2, theta 3, until theta 40. And from theta 2, actually, what is it? From theta 2 onwards, we will calculate them, right? From theta 1, onwards, we'll calculate using this formula. So that formula is applied in here. We won't get any output from running this function. We are just setting the function up. So let's please select all of it. Do not leave anything outside. Up until the last curly bracket and run. And you will notice that R is telling me, hey, I have a function here that has 3 arguments and it's called ARMA2MA. Oh, and sorry, and we need to also we also have to leave an output for a function, right? We use that with return, and the return of this output is going to be a vector that we call theta that will have h plus 1 terms, and those are the responses to the shocks in the variable. So again, we will use this function later, but for now we were just asked to set it up. Now let's move on to question 3. So let's see tutorial 4. So for question 3, we're going to add another function. We're going to do another function to compute IRFs now to both one-off and permanent shocks, right? So we got all these responses in here from the function that we did in 2. We are going to grab from there. Actually, we're going to take an ARMA model, an ARDL model like this one. And we're going to create a function that extracts the coefficients from this ARDL model. Because you guys remember that in order to use this function here, we do need those coefficients as arguments. So we are going to grab those, capture those coefficients in vectors, use those vectors as input in the function ARMA2MA, and well, depending if we want to see like how the shocks are period by period or cumulatively, we can also add a term to calculate that. So let me jump here to R. Question 3. So we are going to set up a function that we're going to call ARDL IRFs. So what it's going to do is to produce the impulse response functions from an ARDL model. The inputs that it has is the estimates of an ARDL, right? We need to run the model, grab those coefficients, and those coefficients will be stored in the model that it's estimated. We need a horizon. The default setting, we can also do these functions. If we make an argument equal to something, that means that that is the default setting. And I'm adding another argument here called CUMIRF, which I'm going to make it equal to true. In this case, it will reflect if I need, or if I'm interested in seeing the shocks like independently, time by time, or if I want to see them accumulated. If I want them accumulated, this argument will be equal to true. So what we're going to do is that we will take the coefficients. So let me show, I think. So for example, if we are going to use a 1-1-2 model, we want to grab these orders, how many lags of the variables in the model we have. So we do that by by grabbing the order in the estimated ARDL and grabbing the coefficients. So we will be grabbing A0, A1, B0, B1, C0, C1, C2, and as many as we have, and we will store that in a vector called coefficients. The next thing is grabbing those coefficients and put them in vectors for every variable independently. So in here, we want a matrix that has a number of rows that is the order of variable 1 plus 1, right? For example, think of x in here. Think of x in here. The order of x is 1, but x produces 2 coefficients, right? So I need to be prepared for that, hence that additional 1 that I put here to also grab the intersects. No, not the intersects, the coefficients for contemporaneous effects, more specifically. And I'm going to grab those coefficients and put it in an argument called a. You guys remember that I need that argument a as an input in the other function, so I'm putting it there. And they are negative. And let me see if the slides will, like for the variable that is in the left-hand side, this will be negative, but I don't know if they will be shown. Yeah, you'll probably have to go through the lecture slides, but for the variable on the left-hand side, they will be negative. So this will capture the coefficients of y if we keep this this notation that we have here. And then we want to get the coefficients for the other variables, right? The exogenous variables in our setting will be x and w, and we want to get them in a matrix. So length order will capture all the orders of these variables. And I want to grab the higher order and put that in a matrix, starting with an empty matrix of 1 plus the horizon number of rows, because remember I have 41 theta's, so I want to have a place to store all those theta's. And well, the number of exogenous variables will be, like in this case, we will have 3 variables, but minus the variable in the left-hand side, that's 2, so that value will be stored here. And I'm not leaving any names for these columns, that's why I'm putting it in here, but this is entirely optional. And I also want to grab the long-run multipliers in a vector. So this is an empty vector that will have a number of slots depending on how many in the exogenous variables I have. In this case, would be 2. And of course, that vector will have no name. That's why we leave that in here. Now, what we're going to do is to circle through each of the exogenous variables. In this case, 2. So it will go from 1 to 2. And I will go and extract those coefficients from the estimation, from the corresponding exogenous variable, and put them in this matrix IRFs. Actually capturing the names of those exogenous variables and replace. Remember that I left the names empty. In this case, I'm changing or updating the names of those matrices, so we know which column corresponds to what responds to changes for what variable, pretty much. So yeah, it's just grabbing the updating the names in the matrix. And remember that we left this argument to be equal to true or false, so we need to set up what's the procedure that this variable will do if we set the argument to be true or if we don't, or if we set it to be false. If we set it to be true means that we want the cumulative sum of these thetas. So what we're going to do is input like the vector A that I got with the coefficients of the endogenous variable and the vector J that I got with the coefficients of the exogenous vector B, so a matrix B, sorry, that I got for the coefficients of the exogenous variables, plus a horizon that I have set to be 40. Go through the process, so I will get a string of the 40 thetas, and in this case, it will not only display me the thetas, but it will add them row by row. So the first value will be the same, but the second row value will be how row 1 plus row 2. The third row will be row 1 plus row 2 plus row 3, and so on. That way we can see how those effects amount over time. But if we don't, if we only want to see how the shocks are from period to period, I will set that function to be false, and I will just leave the string of thetas that ARMA2MA function will generate. And I am displaying also the long run multiplier for each of these variables. The return of this function will be the impulse response functions and the long run multipliers. So let's also generate this function here. That function is put in here. It's all good. And so we will see how they work, like with a real data setting. Now let's jump to question 4, which is now the applied work that we're going to do today. We have that wealth.csv function included in our working directory. Wealth.csv has observations of 3 variables. One variable called CT, which is the log of real per capita expenditure on durables, non-durables, and services. We're just going to call expenditure. So I think these are national accounts, and they are measured quarterly from 1952 through 2006. We have another variable called AT, which we're going to call net worth or wealth, measuring the net worth of the households in this sample, and another variable called YT, which we're going to call income for short. This data comes from this paper, a very, very interesting read if you have the time, trust me. Actually, Rodney Strahan is a lecturer here at UQ. It's a very interesting paper if you want to see how those, like how you analyze long-term, like if you want to complement the conclusions that we're going to get today, by all means. All right, so let's grab a model, right? And let's call it, let's say the ARDL 122. And using the functions that we created in questions 2 and 3, let's estimate the impulse response functions to permanent shocks in wealth and income on consumption, right? As well as the long run multipliers. And of course, to estimate this ARDL, we will need the ARDL function in that package. Actually, I forgot to mention, this is just computational stuff, but this second function, ARDL underscore IRFs, is not going to work if ARMA2MA it's not set up first, because it is nested in that other function. So we need these 2 functions activated at the same time, or alternatively, you can like add more. No, I don't think you can. Or you can build one function inside the other. But I think building them independently and nesting one inside the other is the way to go. So don't forget, you need both of them there. Otherwise, it's not going to work. So let me load the data. We're going to use the same command that we, excuse me. Sorry, my throat's a bit dry. Okay, sorry about that. So we're going to use the command that we have used the whole semester, read.delim. Wealth is lower cases, doesn't have any capital letters in there. First row of variables contain the variable names. So header will be set to be true. And these columns are separated by commas. So hence that argument there. So I'm going to run this. And you notice we have 217 observations of 4 variables. In this case, well, a time indicator in the first column, and then we have wealth, consumption, and income. And we're going to see the dynamic between those 3 variables. So let's estimate how consumption responds to wealth and income using an ARDL model. So the ARDL model first will ask you to put the endogenous variable on the left-hand side, then a tilde, and the endogenous variables separated by pluses, exogenous variables separated by pluses. No particular order necessary here. You can put YT plus AT and the results will be just as fine. But you need to be careful because the first index here in order will give you how many lags you have of CT. The second index here will give you how many lags you have of AT, and the third index of YT. Okay, so we need to specify that with the argument order. And we also need to specify where our data is coming from. And it's coming from my data. So let's estimate and summarize the model to see what we have. Oh, sorry, I'm getting. No, sorry about that. Okay, so I wanted to show you with the slides how the ARDL the ARDL 1 to 2 of this setting will look like. We have CT as explained by 1 lag of itself, right? And 2 lags of AT, so AT minus 1 and AT minus 2, and YT minus 1 and YT minus 2. I will come back to, don't worry about all this work. I will come back to it later, but I just wanted to show you. So the output, let me jump actually from the output here. So this intersect will be capturing this delta 0, this log of CT, first lag of CT. So that will be delta 1 in this case. AT, that would be beta 0. I just gave, by the way, I just gave these random Greek letters. So they won't be confused with the work that we did before. But it's not always named delta or something like that. Just, you know. So beta 0, so it will be beta 0, beta 1, beta 2, gamma 0, gamma 1, and gamma 2. Okay, that's how they are estimated. The second bit of this function, we are estimated, and we are going to use the functions to get the IRFs. So how CT responds to shocks in AT and YT. So let me, yeah, here in R. So what we're going to do is using this function ARDL IRFs, right? Well, actually, no, sorry. We estimated ARDL, and those results are stored in a term called ARDL underscore EST. This name can be whatever, but make sure that it is consistent, right? You can name it estimates, but make sure that you carry the name in all the locations where ARDL EST is located. It's named. That's the input, the main input of our function. in here. We need the estimates of an ARDL model. I don't necessarily need to specify the horizon or if I want cumulative shocks, because they have default settings. So I'm just specifying here. If I want a different horizon by any reason, or if I want I don't want to see the cumulative IRF. If I don't want to see the cumulative effect, just want to see them period by period, I will set this to be false. And I'm going to put the results or the output of that function in an item called IRFs LRM. Okay, so all of this output that is returned, this list of two terms, the input response functions and the long-run multipliers, will be stored in this term in here. So I'm going to run line 105. So this term in here is this IRFs here is capturing all those theta. So theta 0, 1, 2, 3, for wealth on consumption and income on consumption. So that's why it has two columns in here, as you can probably notice. And we have two long-term multipliers. I will get to them when we transform this into ECM. Okay, and now if we want to visualize them, we need to produce the plots. So we have two variables as exogenous. So it's better if we do this in a loop. So it will go from 1 until whatever number of columns IRFs has in here. So it will go from 1 to 2 exogenous variables, and it's just going to plot from a horizon of 0 to 40. It's going to plot the impulse response functions. Oh, actually, sorry, I forgot. This is not theta 1, theta 2. This is theta 0. This is theta 0 plus theta 1. This is theta 0 plus theta 1 plus theta 2, and so on. Sorry, just don't want to see any confusion. So I want to display all of those additions of thetas column by column in a line graph. And in here, I'm just changing labels of X and Y's in the title of the graph, but this is entirely optional as well. So let me run this loop in here, and we will get these graphs, the impulse response functions. So how do we interpret the impulse response functions? We are having a visual guide of how consumption responds to a shock in wealth. So an increment in wealth will cause consumption to increase sharply in the first probably 2 or 3 periods, in this case quarters, right? And afterwards the increment, it's not as sharp, but it will keep increasing until, like, it will keep increasing, but it will be diminishing in the increments as the horizon increases, right? By the first semester, so the first 2 quarters, I think, yeah, by the first 2 quarters, consumption would have increased 12% of the total increment of wealth, right? So if wealth increased by, I don't know, $1 million, we are estimating that the 12% of that increment will be represented in consumption. And in terms of YT, we have a very similar behavior. In the first 2 quarters, the consumption will increase by, but in this case, the magnitude is larger, right? In the first 2 quarters, I'm approximating, consumption will increase by approximately 55%. So 55% of that increment in income will be reflected as consumption. And that increment, that yeah, that marginal increase would be decreasing until it will eventually just be flat, right? So the effect of shocks would be more visible, like closer to the shock. Afterwards, they will be less and less present there. And you guys remember what I mentioned about the long run multipliers? It's the addition of all the effects that consumption and income have on income and wealth have on consumption. So you can see here, for example, the long run multiplier of AT is 0.26. So you can see how after 40 periods, that's 10 years. So 40 quarters, that's 10 years. It will eventually just be flat. So the cumulative effect of that, the maximum hike that this point will have is at 0.27 approximately, which is what we are seeing in here. And for changes in income, the total effect is a bit larger. So after in the long run, 78% of that increment in income in here will be reflected in consumption. Okay, so maybe that helps visualize what I meant by beta, by those betas that we got before. Now, next question will ask us to estimate the ECM representation of the ARDL 122 model that we have and report the results. Of course, this calculation is independent to the ones that we got before. So let's compare how these long run multipliers will look like to the ones that we got in the previous result. And these are the functions that we need to use in order to get them. So remember that I mentioned that the error correction model is split into short run and long run terms. The work that we do in R, unfortunately, it's also split into those two horizons as well. So let's calculate the short term first. So we used RECM, right? I don't know what the R stands for, but ECM is for error correction model of the ARDL that we estimated. And we're going to set up case to be equal to 2. There are many variations of the error correction model. In our case, we want, let me show you something in here. So this is the way that the ECM is transformed from an ARDL 1 to 2. I'm just going to display this so you guys can go to the video and pause and do it yourselves, but I will not be stopping to show. Sorry, let me start over. So this is the first procedure, this is the second step of the procedure, and this is the third. So yeah, please take time to practice this on your own time. So I am setting first a function, or no, not setting a function, like asking R to estimate these short-term bits, and setting it to case be equal to 2. That means that the constant is just a constant term. We don't have any time varying terms, and we have a constant in the long run term. We have different ways to express this depending on how gamma and mu look like. In this case, so case equal to means that both gamma and mu are set to be constant terms, and that can be estimated. We can also set them to be equal to 0, and all of that depending on what we want to do. But in this case, that's what we do. So let's get that error correction model, and we get the estimates. Actually, case equal to, I think it sets also gamma to be equal to 0, if I'm not mistaken. So we get estimates for delta AT. So we have beta 0. Estimates for the log of, for the first lag, sorry, the first lag of AT. So that is beta 2. Estimate of YT, delta YT actually, so that's the gamma 0. And the estimate for delta YT minus 1. So this will be gamma 2. So when reporting it, remember, we will need to flip the signs of both beta 2 and gamma 2. Lambda, sorry, not gamma, lambda 2. And we also get in this ECT, we get alpha. We get the long run, the adjustment parameter. That's estimated here. Remember, we needed it to be negative. I mean, not that we need it, is that if alpha is negative, these three variables share a long run equilibrium. So that's actually why it will eventually, like these IRFs will eventually stop growing, will just become a flat line again, right? That means that they share a long run equilibrium. But this, the coming back to equilibrium is quite slow. It's 0.036 approximately. So it will take a while to come back to equilibrium. That's why the horizon, after such a long horizon, it's still getting there. It will take a few more periods in order just to be completely flat. Now, if we want to see gamma, mu, and beta A and beta Y, so the long run multipliers, we need to use the multipliers option in here. So let's get the multipliers and display in here. This intersect, this one is mu. We have beta. Actually, let me. Sorry. Let me change this. This is not beta X, this is beta A, right? The long run multiplier of wealth on consumption and income on consumption. So beta A will be this, and beta Y will be this. And if we compare to the long run multipliers that we got before, well, they are the same value. So our functions were well defined. That's always good to know. Now for question C, well, actually, for question C, we are going
I have a
now
question.
obtain the impulse response functions, but including confidence intervals. Okay, that's another function that Eric already worked by himself and put in the in that file that I mentioned that I will ask you guys to download, this ARDL_IRFs_CI.R. So please make sure that you have it and you load it in your working directory. All right. Let me see questions. The questions now. Okay, so let's explore what's in this ARDL_IRFS_CI function. It's an expansion of the function that we did in question 2, well, questions 2 and 3 actually. But now it's not only providing us with the thetas, but it's also going to give us the lower and upper bound of a confidence interval of whatever confidence level we set. The default set is 95%. Of course, we also get that argument that if you want to get the cumulative shocks or not. So the default, it is true. We also need to input the horizon and the estimates from an ARDL. So it's pretty much the same inputs that we had before, but now we are adding the confidence as the confidence level as another argument, another input. And as output, we are going to get 3 matrices of the lower bound of theta for each of the variables. In this case, we will have two variables, right? So we get two matrices. What's the lower and upper bound for those shocks, for example, on wealth on consumption and income on consumption. Middle is just thetas, right? It's the middle draw there, and upper bound the opposite, but now yeah, for all those two variables. So yeah, k is the number of independent variables, in our case 2. So we will do that. Now, in order to use that function, if we use the command source, what source is going to do is that it will grab an R script, and whatever variable, data frame, function, whatever thing that it's defined in that R script, R is going to bring it into our environment. Okay, it's not only for functions, it's for everything. So if you like, you can also store the functions that we did. These are MAC2MA and these ARDL IRFs. Just leave them in an independent R script, and we can call from them without any problems. So where was I? So let's call all of those items, all those objects in this R script, and let's bring it to this one. In our case, we have these two functions, ARDL underscore IRFS CI and ARMA2MA underscore grad, right? So they are expansions of the functions that were already generated. Not going to stop on like how are they built, because it's out of scope. Just again, for peace of mind, you will not be asked to produce these functions. We are giving these functions for you. So if you like need to work with them for your assignments or something, they are programmed so you can use them like with your own data or the data that you're provided without having to do any editing. Okay, so hopefully that will not be a problem. Now, let's use that function on the results that we have from ARDL, and we are asked to do this at 68% confidence. Confidence level. I explained last week why 68% is also a valid confidence level in terms of decision making, right? Remember, we discussed this in terms of risk profiles. Like you want to, like when you are checking at the 95% confidence interval, you get quite a broad picture. But when you like reduce it to 68%, you can see like some other scenario that can help you. Like 68%, it's usually quite accurate in terms of forecasts, as we saw before. So it's also a measure for risk adverse users to see, okay, this is quite likely, and I like what I see. I can afford these losses, or in order to attract these possible earnings. So that's why we use 68%, but more on this on last week's tutorial recording of how 68, like how is it determined and all of that. So let's get those 68% confidence intervals. I don't remember. No, I didn't run this. So let's run line 1 to 9. It will give me all these thetas for the for the actual values, the lower bounds and the upper bounds for the two variables. That's the three matrices that are stored this in these lists. And let's plot them and let's see how they look like. So let me wipe these graphs from here, and let's do this. So what we're going to do is to go by each of the columns of the list that we have there, and grab the information from the item lower bound, upper bound, and MD, and put them in the same graph. So we have like this black line is the same that we got before. but it got a little bit shrunk because now the range here of values is quite larger. It's quite broader. So so this one is how consumption responds to shocks in wealth. Sorry, I always get those three variables mixed up. And the next one is how consumption responds to changes in income, right? We noticed that for the first 2 or 3 periods, let's start with wealth. We were predicting that wealth will have taken approximately 12 to 15% of the increment. Consumption would have taken 12% of the increments in wealth, but we see them going like anything in between 0.9 to 0.15, something of that sort. As the forecast horizon increases, these confidence intervals will get broader and broader and broader, because those thetas will also capture some sorry, I forgot the word. Some uncertainty. Got it. Some uncertainty. So as you add more and more and more uncertainty, that's why those intervals will become larger and larger. We were also observing that in the first 2 or 3 periods, consumption will have taken approximately 55% of the increment in income. And we also observed that to be like anything in between 0.5, maybe 0.65 approximately, with 68% confidence. These two behaviors are very similar, and the behavior is very similar as well. The confidence interval will get broader, and we also kind of saw this last week, like as the horizon that we are observing gets larger, it's more difficult to get accurate estimates, right? Especially given that we are not increasing our sample size. This is a limited sample, so that uncertainty will be just added up and up and up. Also, this is a sign also that our estimates might not be stable. So let me go back to the results here. The coefficient for the lag of CT is very close to 1. So that's another, this is something that needs to be noted, and means that our model it's not unstable, but it's close to instability, and that's not good. So that might be another, it makes sense that these coefficients get broader and broader. It might be that the model is not stable. Yeah. So yeah, but long story short, we can conclude that it's not very smart to try to predict how these changes will be like 10 years in the future. It's always good to stay, even if the model is not stable, it's always good to stay in a close by range when we want to see, like for decision making, right? Of course, it's good to have the whole picture, but in terms of decision making, it's good to focus only on the horizons that are closer, not too far in the future. I hope that makes sense. Let me see if I'm not forgetting anything. No, I think that's like the main thing, and that interesting dynamic we already explored in here, right? This is what we want to, this is the best picture that we have of how consumption responds to changes in income and wealth, right? Now, we got these impulse response functions, and we want to compare these middle values in here. Actually, I didn't show that question. For question D, we want to compare those middle values to the IRF estimates that we got in part A, right? When we didn't have the confidence interval. So we want to see if adding those confidence intervals or the procedure to do will change dramatically, or the values are too different. We will not, like, we are expecting that to not be the case, but we need to double check that. And well, the way to double check this is to calculating the norm between those two values, those two strings of thetas. And those two, I want to explain this so it's not very confusing. So we have those two strings of thetas calculated in question A and calculating now in question C. We could take difference of those two values, but it might be the case that there might be some discrepancies, as like rounding errors. So it might not be the best way to measure. So in order to avoid that, we are going to calculate the norm between those two vectors. The norm is an operation in matrix algebra that it's equivalent to difference, but instead of two numbers, it's for two vectors, right? So let's calculate the norm of these two strings of values. So the difference of terms in the thetas that we got from the function IRFs and the function that we did in this question, it's 0, so they are the same value. So actually I deleted the plots, but I should be able to get them from here. So these lines in here are the same lines, the black lines in between in here. And we, with this result, we confirm that they are the same. Now let's move on to question E. In question E, we want to get the 65% confidence interval, but now for the long run multipliers, right? You probably noticed that like the long run effect is quite, like it's not a constant term as we estimated before, but it also can be as high as this value or as low as this value. So we want to see if the 68% confidence interval for this long run multiplier would be the same as if we take this result and we get a 68% confidence interval based on the estimate of the long run multiplier and the standard error. So we're so we're going to grab these results, calculate a 68% confidence interval, and we calculate and we compare to these values that we got from the function. So whoops, sorry, wrong slide. So in order to do that, in order to calculate a 68% confidence interval, we need to obtain the 84th percentile of the normal distribution. The way to calculate that percentile based on the confidence interval is with this operation. So 68% in the normal distribution of the normal distribution is stored in the 84th percentile, and we want to get the value from the normal distribution, from this, like the set score from the 84th percentile, and we'll store it in a value called C. So this is the critical value on the normal distribution. Remember, in order to build a confidence interval, we need the critical value. So let's construct this confidence interval. We will grab the estimates from the long run multipliers. In this case, we grab estimates 2 and 3. So not this, but here, sorry. So from where is it? From these results, right, from ECM long run multiplier, we're going to grab these estimates 2 and 3 and standard errors 2 and 3. We're going to put them in two terms here. Now, in order to get that, we will also need a matrix because all of these are stored in matrices. So we need a matrix of ones that has 3 rows and 1 column. And we also need these set scores in a matrix. So I will have the negative value of this, then a 0, and then a positive value of this in a matrix that I'm going to call C set. And then we do the operation to calculate the confidence interval. And we get those results, right, in a matrix called long run multiplier confidence interval. So let me run up until this point to see what we get. What is it? In here. So it's here showing me the lower bound, middle term, and upper bound of the 2 long run multipliers of the variables. In here now, I'm just going to change the row and column names to make this matrix more informative. And in here we can see, okay, the long run multiplier, the middle term estimated is the same that we estimate earlier, which is good. And this is the lower bound and upper bound. So worst case scenario, after like a lot of periods have passed, 14%, 15% of the change of the increment in wealth would be transformed to consumption, and 60. This is worst case scenario, right? In 65% of the increases in the income will be reflected. Actually, this is not correct. This is not CT. This is YT. Yeah, and worst case scenario, 65% of the increment in income will be reflected in as consumption. Best case scenario, those percentages are way higher. Now let's compare these. Like this is the upper and lower bounds that we got from the results on the estimate. Now let's compare to the results that we got from this. So what we're going to do is grabbing these last points, hence this indexing here of the lower bound, the middle term, the upper bound, but from the confidence, the IRF functions that we generated with the function that Eric uploaded. So we are going to get a similar matrix that as we have in here, so we can compare. And we can see how different the values are, right? Middle terms are quite similar, so that's okay, but the upper and lower bounds are not as accurate. Just hang on, just give me a sec, sorry. Right, so the discrepancies are quite high. Let me see if I'm not missing any more discussion in here. Oh yeah, some causes for these differences. One might be that we have very limited data points. We only have 200 data points, so that sample might be too small, hence the wide variation that we are estimating. So less data points means more uncertainty in our estimates. And I mean, this is not uncommon, but like this will happen all the time because first it's difficult to have a lot of observations when working with data, And second, well, like these forecasts in such long horizons, they always need to be taken with a grain of salt. Okay, please remember that. It's always good to stay, like I mentioned before, as short run as possible for decision making. All right, let's move now to question F. Now we're going to do some model selection a little bit. We didn't do that. We were just given the ARDL 1 to 2 to work all of this because, you know, when we do model selection, we get a set of models. So doing all of these for such a large, like 4 or 6 models might be too much. So I respect this order of working for this tutorial. So let's construct an adequate set. So let's do model selection. What I'm going to do is to select combinations of P, L, and S that will go from 1 to 5, 0 to 4, and 0 to 4. So the first term, the first lag of the ARDL can be anything from CT-1 to CT-5. So it can be combinations of that. It needs to start at 1 though, because this can't be 0. Like the lags of the endogenous variable cannot be, like we have to have at least 1. But we don't need like the other variables, so we will start those from 0. Meaning that we will just take contemporaneous effects and we will have up to 4 in here. So we will have, I don't know, 1, 0, 0, 1, 0, 1, 1, 1, 1, blah, 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 until 5, 4, 4. So all of those combinations, as we did last week, we will nest loops, right? P being the lags for CT will go from 1 to 5, L being the lags of AT going from 0 to 4, and S being the lags of YT will go also from 0 to 4. We'll put an index. This is easier than the index that we used last week. If we want to find a way like to transform the work that we did last week using these new indexes, I will be able to help with that. It will start at 0, and at every run of the loop, it will increase. Because remember, we create this matrix of selection criteria. So at the first run, it will fill this line, then the second run will fill this line, and so on until it goes from those 125 models all at one, like recursively. So what we do is that the first model will be 1, 0, 0. That will be in row number 1, right? 0 plus 1 is 1. Of the selection criteria. It will store whatever number P had, so 1, 0, 0, and the AIC of that model and the BIC. Of course, we need to estimate that ARDL. The index for the orders will be in here, and we are also, so we don't have to estimate them again. We are also storing those results of the estimation in a list that we call ARDL EST empty, and we're going to fill up with all those estimates. Lists are super useful in R because you can, like, remember that I mentioned that they were like a chest of drawers. You can put anything in them, and R will have items of different natures in the same object, and I think that's great. So let's do all of these. Let's run the loop, and let's see how it's taking a second. When R shows this blinking bar, means please let me work. So we're going to see how this information criteria matrix will be filled with all those values as they run the loop. So starting from 1, 0, 0, AIC and BIC are stored, blah, 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 all on that, all the combinations until 5, 4, 4. Of course, comparing 125 models might be too much. So we're going to do the same as we did last week and only look at the first 10 in terms of AIC and BIC. And we will get this, oops, sorry. We'll get these two tables. So as we did last week, we will find models that are in both lists. In this case, 122, 132, 222, and 123 are in both lists, but Eric instructed us to take the first 6 in terms of BIC. I will be careful because ARDL 102 and 112 are not the best in terms of AIC. They are not too far away though. They are quite far away, like 1,600 or 1,590. For 98 to 94, not too different, but this one, 88, that might be too high. Remember, we want the lowest AIC possible. So we were instructed to work with the first 6 in terms of BIC, but, oh, excuse me. But yeah, I would go with the four specifications that are in both lists. We're going to keep this 6 though. So we're going to store those 6 specifications, so the first 6 rows in BIC, and we're going to keep them as an adequate set, right? Those 6 values are in there, so we have all those indexes in there, all those combinations of blacks there. Now, this is quite interesting what it's done in here. What we're going to do is match these. Let me check something. We're going to match the contents of these rows of this data frame to the rows of the big one, of this one, the 125, in order to capture what, like, for example, 122, what row number does 122 have in this matrix is 13. So to save that index in here. Which one is 112? 112 is number 8. So we're going to keep those row numbers in here because later we can match it through like with the components in the list where the estimates are stored, and that way we can grab the models without having to like rearrange these orders in here. I think it's quite smart what Eric did in here. And you can notice that the first term in here is the 13th in the IC matrix. This one is the 8th. I showed you that. This one is the 18th. This one is the 3rd. This one is the 38th. And this one is the 14th. Because if you, like I'm going to repeat myself a little bit. If you notice, all of these estimation of models are, we estimated 125, and all those coefficients estimated are stored in this list. So later we're going to say, okay, please give me the results on the estimation stored in the 13th drawer, right? To keep with that analogy, then the results in the 8th drawer, and so on. Okay, so we have subset to these 6 models. The next thing is to give a quick look at the residuals. So we each of these estimations actually, where are they? Sorry. Each of these estimations will store the residuals, right? So we're going to look at those residuals and see, like in terms of the graph, to see if we identify any autocorrelations in there. Let me start from the first model. So 122, we notice that there is no like a structure evident in here. None of these lags, none of these autocorrelations are significantly different than 0. So that's good. We are, this is like the visual way to do the Young-Box test, by the way. All of these, everything else, this is just customizing the labels and like the zoom that we give to this graph, by the way. So 1 to 2 is fine. 1, 1, 2, even if this one was getting a bit high, it's fine. It's not significant, so that's good. 1, 3, 2 again, fine. 1, 0, 2, we have 1 in here. We shouldn't. So for me, that would be enough evidence to discard that model and just move forward with a set of 5 models, but I'm instructed to move forward with all 6. 2, 2, 2 is fine, and 1, 2, 3 is also fine. So that's the models that we have selected. Now let's check the dynamic relationship between expenditures and wealth. So we're going to focus only on CT and AT. We're not going to do anything with YT, with all these different specifications, to see if the inference that we draw from this is consistent through different specifications, which means that our conclusions are robust, right? So let me get ready here for a second. Now, jump to R to question G. Now let's, what we're going to do is to check the impulse response functions at 68%. We're going to like repeat the process that we did before, but for each of the different models, right? So we're going to get, let me see if they're still here. These graphs, but this one wasn't for the 1 to 2, so we're going to do for all those 6 specifications, but we are only going to get this one to AT, right? We're not concerned with YT. I think it's for time purposes. So we need to press forward a little bit in this. So I'm not going to stop too much in this code, only mentioning that like the confidence intervals are obtained using that function that we got from the R script. The results are like the estimates from the ARDL are captured from this list of 25, and we are getting from the index using these indexes that we captured before. So that makes this line of code way easier. We're getting the lower bound, middle term, and upper bound of those confidence intervals, and this line in here is setting which one is the minimum value from the lower bound and the maximum value in the upper bound. And in order to get a large number of values to compare, we set this minimum value to be infinite and maximum value to be negative infinite. So these values will be put in here. So yeah, I'm not gonna stop there. Don't worry too much about this. This code is completely replicable. So if you want to work on your own, like on your own assignments, it should work just fine. Or I or the other tutors can help you guys out doing all these adjustments to the code. So let me run all of these. And by the way, we are working with the first column of this, which corresponds to responses of AT. So if you wanted to explore how it responds to YT, we will, it's the second column, so we will need to change that. So let me run this, and in here, I am capturing the, wait, hang on. See, in here, I'm capturing all these upper bound, thetas, and lower bounds for these input response functions for the 6 specifications that I worked on, right? So let's plot them and see what we can observe from this behavior. 2, 3, 4, 5, 6. So these are the different specifications here. But you can notice, like, the first thing that we notice in a couple of these is that in the long run, like in this case, for example, and in this case a little bit, and in the first model that we got 1, 2, 2 also, we are predicting that the response from the response on consumption from changes in income on wealth, it's actually predicted to be negative at some point of the confidence interval, which is something that makes little sense. If I'm completely honest, because like economic theory and common sense pretty much tells us that the higher the wealth of a household, the more they will be affording to consume, right? So at the very least, it should be a positive number. So this is one indication that our results in the long run, maybe these specifications are not stable, one thing, and that the further we go in the future, the uncertainty at some point gets unmanageable. So it's good, like, to avoid that. So yeah, the behavior in the short run for most of these models is quite similar. Not for 112, for 132, yeah, it's quite similar. For 102, it's not. And 222 is the same, and 132 is the same. You notice, for example, that in the AIC and BIC selection, I propose to drop 102 and 112, and we can see here that they might be not good models, so we were better just working with the other 4. The behaviors are very similar. Excluding this and this, the other 4 graphs, the behavior is quite similar. Let me see the upper bound. Yeah, the upper bound here is around 0.5, so we can also conclude that, like, all our models are giving us the conclusion that by 10 years in the future, 50% of the increment in wealth will be consumed at most. But yeah, so that result seems to be consistent. In the short run, like I mentioned before, we have like 2 cases, right? In the models that I would have kept, the behavior is very similar. In the first semester or so, approximately 15 to, yeah, approximately 9 to 15% of the increment in wealth is reflected in consumption. I don't think it will ever be above 20% in any of the models. Nope. So that result is consistent. Yeah, so keeping all the models that I would have kept in the first place will have given me actually robust results. So it's always recommended to be quite strict on your model selection. But yeah, main conclusion is this is like 10 years in the future is too uncertain. So it's always good to work with smaller time frames. Okay, guys, that's all we have for today. Thank you so much for your attention, for like bearing with me with the technical difficulties. I hope my signal wasn't too bad. But anyway, the recording will be uploaded by this weekend. So make sure you drop by there. Make sure you like work, especially in the ECM transformation. go through the solutions guide. That will be available on the weekend, so you can like get more insights on the conclusions and all of that. But for now, I'll stop. So thank you so much for today, and I will see you guys next week.